In this video, I want to quickly go through how to graph a parametric equation, how to label initial and terminal points, how to know in what direction the parametric equation is going, and to be able to change it to a Cartesian equation. These are all kind of pre-calculus skills, not the course pre-calculus, but the calculus you're going to need to be successful with parametrics. First of all, we're going to graph, and I'm going to do that with just a little table you see here. I think this is the easiest way to start graphing by hand. I've given you a y and an x. I probably, to be nice, would have given x first, but this gives us both our horizontal and vertical components, and I've given you the domain that time is greater than 0. So let's start with x, and let's just pick a couple of t values, maybe like 0, 1, 2, 3, 4. Maybe that'll be enough. Okay. So negative t squared. X is negative t squared. Well, negative 0 squared is 0. 1 squared negative is 2 squared negative is negative 4, negative 9, and negative 16. Okay, so those are our x components. Now let's go to our y components. 2t plus 3. Well, 2 times 0 plus 3 is 3. 2 times 1 plus 3 is 5. 2 times 2 plus 3 is 7. 2 times 3 plus 3 is 9. And 2 times 4 plus 3 is 11. These make up our coordinates. T never appears in the graph. Okay, that variable never appears on my graph. All we're doing is referencing, and that's why that diver example I think is so important. We're getting a path referenced from time, but time is not on the graph. So my first point is 0, 3. My next point is negative 1, 5. My next point is negative 4, 7. My next point is negative 9, 9. And my next point would be off the thing, so I'll just draw that. Now, I talked about labeling an initial point and a terminal point. Initial point just means what's the first point. Well, because I said it's only from t greater than or equal to 0, when t is 0, that makes up our initial point. Another thing that's kind of nice to do with parametrics is draw an arrow that shows what way the path was going. Because parametrics are used to map paths, to be able to say, okay, here's where it started, and then it was moving in that direction. In this case, we aren't going to have a terminal point because the graph had no ending. I didn't have an end to t. I didn't have a range of t values. The one other thing I want to mention here is turning something into what's called a Cartesian equation. Cartesian equation simply means a y equals. Easiest way to make it a y equals equation like we're used to is to rewrite the x equation in terms of t. So t is equal to the square root of negative x. And then take that and substitute that in to y. So we end up with y equals 2 times the square root of negative x plus 3. And this is a Cartesian equation that would give us the same graph, which it certainly looks like a square root function that's been reflected and shifted up. All right, let's do the next one. Now I do give you a range of x and y. So it went from negative 1 to 2, so negative 1, 0, 1, 2. So 4 plus negative 1 squared is 5. 4 plus 0 squared is 4. 4 plus 1 squared is 5. 4 plus 2 squared is 8. Okay, the y values. 5 multiplied by negative 1 squared is 5. 5 multiplied by 0 squared is 0. 5 multiplied by 1 squared is 5. 5 multiplied by 2 squared is 20. So that one will be off. So our first point is 5, 5. So that's right here. Our next point is 4, 0. And our next point is back at 5, 5. And then 8, 20, way up here somewhere. So what happens here is it goes down, comes back up, and then goes. So this is our initial point. This is our terminal point. And what happens is it goes down and comes back around. If you were drawing your arrow, it comes back on the same point. Okay, if you were drawing the path. Now, this is something that's new and different and kind of interesting that you can come back to the same point, but doesn't that make sense? Paths do that, where you go one way and then come back to the same point. So hopefully it makes sense that that's very possible. And once again, we can, think about a Cartesian equation here. We could say, well, you subtract 4, take the square root. So you could write this as t equals square root of x minus 4. Plug that in. 5 multiplied by that square becomes 5 multiplied by x minus 4. Like that. Now, it certainly looks linear. The thing I drew looks like a line, all right, with a slope of 5. So this is good. Unfortunately, we're missing information. That's one of the reasons I don't really like to switch to Cartesian, because we're missing the fact that it came down and went back over itself. We're missing the domain, which we could add. We could certainly say, well, it's only going to work when x is greater than 4, or, because that's where it starts right here. We could add a domain statement, but we're missing information. And that's why I don't really recommend switching to Cartesian. If it was given to you in a parametric equation, there's a reason for that, and it's worth keeping it in that. Lastly, let me graph this last one. If I can create myself just a little bit of room, maybe. Anyways, let's go. We have -2. -1, 0, 1, and 2. Sorry, it's getting a little cramped there. So x is t plus 1, so -2 plus 1 is -1, 0, 1, 2, 3. Y is -3t plus 1, so -3 times -2 plus 1 is 7. -3 times -1 plus 1 is 4. -3 times 0 plus 1 is 1. -3 times 1 plus 1 is -2. -3 times 2 plus 1 is -5. Okay. So again, we have an initial point here, but we won't have a terminal point. So let's graph these. -1, 7 is up here. 0, 4 is right here. Remember, t doesn't appear on the graph. We only look at the x and y coordinates. 1, 1, 2, -2, 3, -5. So, whoops, I went a little bit far. Let me see if I can't. So this shouldn't be here. This little part up here, I just drew a little sloppy. The initial point is there in blue, and it's actually just starting there and going down. There's no terminal point. Okay, and once again, we could say, well, t is equal to x minus 1, substituting that in, so -3 multiplied by x minus 1 plus 1. And it certainly does look like a linear function here with a slope of -3. But again, I recommend not doing that where we lose information. So this is the basics on parametrics and how to graph them, to label the points, and to come up with the Cartesian equation that mimics it. Okay, so these are all pre-calculus skills. Now I want to do one more video with just a little bit more of this, but this is really the beginning of what we need.